So far we considered some special cases. Today we will consider multiple dielectric layers. This has a lot of practical applications, as I was mentioning on Monday in our online lecture. So the foundation still remains the same. That is, we have an interface which comes separating out region 1, region 2, and then there's an incident wave, and there's a reflected and a transmitted wave, and the ratio of transmitted to incident wave is tau. We can express it in terms of eta 1, eta 2. These are the intrinsic impedances of the two media. And similarly, we can write down the ratio of amplitude of reflected wave to the incident wave as reflection coefficient, which is equal to eta 2 minus eta 1 upon eta 1 plus eta 2. We have seen this several times now. We will see how to apply this to solve a problem which looks like this. We have three regions or three media, medium 1, medium 2, medium 3. All three are lossless media. Therefore, sigma 1, sigma 2, sigma 3 are all 0. And the first medium is characterized by permittivity epsilon 1, mu, and permeability mu 1. Second medium has permittivity epsilon 2 and permeability mu 2. And the third region is characterized by epsilon 3, mu 3. We have aligned the coordinate system such that the first interface is at z equal to minus d, and the second interface is at z equal to 0. This is by choice. It could have been the other way around also. This is more convenient for us. Beyond z equal to 0, that is z greater than 0, there is no discontinuity. And in the region z less than minus d, again it's homogeneous. There is no discontinuity in that. Now the question that we are going to ask is, how do we calculate the behavior of this problem? For that, we will assume some incident field EI, and we have an associated with a magnetic field HI, and we know that intuitively there will be a reflected wave characterized by ER and HR, and the total field in region 1 is given by E1 H1. This equation is well known to us now. We can almost write this equation the moment a problem is posed. Only thing that we have to decide is what is the polarization of this wave, and we have consistently used X polarized wave, so we will continue to use X polarized wave. We could have jolly well made it Y polarized. It wouldn't have made any difference. In fact, any polarization would have been all right. Now, this is region 1. What do you think about region 3? In region 3, we will have only a transmitted wave because this is homogeneous and it's going to infinity, no discontinuities. We don't need a reflected wave there. Therefore, we assume that E3 is given by AX cap E3 e to the power of minus j beta 3 z. This is an art. This is the art that you develop by the knowledge of science. As you gain experience, you know in which region what to assume so that the solution comes out to be clean and neat. If you assume something more than what is necessary, we have seen before, all those coefficients will go to 0, unnecessary components will automatically go to 0. If you assume something less, we have also seen that before, the solution becomes absurd. Now, think about it. What do you think would happen in region 2? Yes, region 2 requires a forward wave and as well as a reflected wave. So we don't call it reflected or incident, we call it by terms E2 plus H2 plus, representing the wave going in the positive z direction, and we give the symbol E2 minus H2 minus for a wave going in the negative z direction. This is a very convenient choice. We don't worry about what is incident, what is reflected, because everything is all jumbled up. Those equations can be written as E2 H2 given by the middle set of equations here. Are you all convinced how we write these equations? If you are convinced, the next question to you all is, what do we do next? Yes, we have to satisfy the boundary condition. What are the boundary conditions? Continuity of electric and magnetic field, the tangential components of that. That is E1 equal to E2, because E1 is AX E2 only has x component. X component is tangential to that surface at z equal to minus d. Therefore, E1 equal to E2 at z equal to minus d. H1 equal to H2 at z equal to minus d. Similarly, E2 equal to E3 at z equal to 0 and H2 equal to H3 at z equal to 0. How many unknowns do we have? We have 4 unknowns. What are those? ERO, E2 plus, E2 minus and E3. These are the 4 unknowns. What are known things to us? EIO is known and therefore there is no issue with that. There we have 4 equations, 4 unknowns, 4 equations. You have a long sheet of paper, lot of time with you, keep solving, eventually you will find a solution. I hope so. But we are engineers, so we try to find shortcuts. We try to innovate new thoughts, new ways of solving such problems. So today I'm going to show you several methods to solve this problem. You will be surprised the versatility of several techniques that we have learned in different domains, how they can be applied if you know the logic behind it. Take the first one. It's called wave impedance approach. So we define wave impedance as total Ex upon total Hy. So this is how we define wave impedance, right? So we know in region 2, E2 is given by this quantity, the forward E2 plus times e to the power of minus j beta 2z plus E2 minus e to the power of j beta 2z. And in region 2, H2 is given by summation of positive going magnetic field and positive going wave and negative going wave. Good. Now we can take the ratio of these two. For the moment, let us consider a single wave propagating in an unbounded medium. Just imagine that. That means either it can have a positive z going wave or a negative z going wave. If it has a positive z going wave, then we have quantities E2 plus e to the power of minus j beta 2z and E2 plus upon eta 2 e to the power of minus j beta 2z. Take the ratio of those two, what you get? The intrinsic impedance equal to eta 2. What will it be for a negative z going wave? Yes, it will be minus eta 1, eta 2. So for a negative z going wave, the wave impedance will be minus eta 2, whereas for a positive z going wave, the wave impedance will be plus eta 2. We'll remember this, it will be useful. Of course, if you take the ratio of E2 and H2 together for a combined both the waves, positive and negative, we get a nice result, eta 2 e to the power of minus j beta 2z plus gamma e to the power of j beta 2z upon eta e to the power of j beta 2z minus gamma times e to the power of j beta 2z. Have you come across this in transmission line? Yeah, you have. Very similar looking equation. In fact, it is the same equation. No difference at all. The way we write it is slightly different. The symbols are different. Instead of characteristic impedance, we are using what's called as intrinsic impedance, and instead of voltage and current, we are using electric field and magnetic field. That's all the difference. Form is exactly the same. A beautiful result, very useful result. We'll remember this. So this is the wave impedance of in the region 2, where we have both positive z traveling and negative z traveling wave. Okay. And gamma is E2 minus upon E2 plus, which is the reflection coefficient at z equal to 0. Right? That's how we define this. This is perfect. This is good. Now let's look at the more problem that we are trying to solve. We have 3 regions. Epsilon 1, mu 1 has intrinsic impedance eta 1. Region 2, epsilon 2, mu 2 with intrinsic impedance eta 2. Region 3, epsilon 3, mu 3 with intrinsic impedance eta 3. And we also written field equations for region 2 given by these two equations on the top of the screen. Now what do? We will look at the wave impedance in region 2, which is E2x upon H2y, which is given by that result by simply taking the ratio of the two equations on the top. Now, what is gamma 3? We already said it is E2 minus upon E2 plus. And look at that. Where is that? It is at z equal to 0. At z equal to 0, what is gamma 3? It is the reflection coefficient which we had proved earlier, which is eta 3 minus eta 2 upon eta 3 plus eta 2. It is a reflection coefficient experienced by a wave hitting that interface at z equal to 0. Alright, good. With that, we will now compute what is the impedance at z equal to minus d. And that's very easy to do. We know z at any z, put z equal to minus d, you get an equation for z of minus d, which is eta 2 times 1 plus gamma 3 e to the power of minus j 2 beta 2 d upon 1 minus gamma 3 e to the power of minus j 2 beta 2 d. How did we get this result? We simply took out e to the power of j beta 2 and then it's straightforward to get this result. Now, what is reflection coefficient? Reflection coefficient is z input minus eta 1, that is the impedance of region 1, upon z of minus d plus eta 1. This is something like zl minus z0 upon zl plus z0. Remember that result? Exactly the same result here. So this is the reflection coefficient, which you can straight away, can it be done straight away? No, you may require to do a bit of jugglery to show that gamma in is given by gamma 1 plus gamma 3 times e to the power of minus j 2 beta 2 d upon 1 plus gamma 1 gamma 3 e to the power of minus j 2 beta 2 d. It's not very difficult, but I would want you to show this result. In today's talk, I'll be leaving several such derivations for you to do. It is important that you please do it on a piece of paper. Convince yourself that these equations are indeed correct. There will be certain tricks at times. You will figure it out when you're trying to solve when you're trying to derive these results. And what is gamma 1? This lecture is not. Okay, let's try another approach. This method is an iterative method or multiple reflection method, where we almost play a game to find the reflection coefficient. Suppose there is an incident wave with unit amplitude. It is hitting on some interface at the first interface at z equal to minus d. The slab is has a thickness of d, and propagation constant in that medium is beta 2. Therefore, the electrical distance theta is beta 2 times d. And if you remember that e to the power of minus j beta 2d can be written as e to the power of minus j theta. Good. With that knowledge in the mind, the background, let's see what happens to this wave of unit amplitude hitting on the left surface. Some part is reflected back. How much by how much? By gamma 1. What is gamma 1? It is eta 2 minus eta 1 upon eta 2 plus eta 1. Eta 2 is the intrinsic impedance of the middle region, medium 2. Eta 1 is the intrinsic impedance of the left region, medium 1. Now, a portion of it comes back, a little bit of it goes into region 2. How much? Tau 21 goes into region 2. What is tau 21? It is 2 eta 2 upon eta 2 plus eta 1. Remember that one interface problem? We are using the same result here. And what happens to this wave that has gone into it? It travels a distance of theta, therefore it gets multiplied by e to the power of minus j theta. Here again it encounters another discontinuity. And what happens at this discontinuity? A portion of it called tau 32 goes into medium 3. And tau 32 is 2 times eta 3 upon eta 3 plus eta 2. Just imagine for a moment, if I were to have one more medium next, beyond, z equal to 0, you can apply the same principle and start adding up, not an issue. But I want to know what is the amplitude of the wave coming out of it, which is the product of tau t1 multiplied by e to the power of minus j theta multiplied by tau 32. That's what comes out. Now, don't leave it that way. A portion of it got traversed or transmitted to region 3, but at z equal to 0, a portion of it will get reflected as well. By how much? By gamma 3. What is gamma 3? Eta 3 minus eta 2 upon eta 3 plus eta 2. Yeah, can you see that? Yes, eta 3 is the third medium minus impedance of the second medium and so on. And this travels back with a distance of beta to d or e to the power of minus j theta, and comes out of the medium, comes out into medium 1 with a factor tau 1 2 given by 2 eta 1 upon eta 1 plus eta 2. And therefore, what is coming out into region 1 or medium 1? It is tau t1, start from the top, tau t1 e to the power of minus j theta, gamma 3 e to the power of minus j theta times tau 1 2 comes out of it. Are you following it? Now what happens? A portion of it gets reflected back at the interface at z equal to minus d by how much? Gamma 2 times that. And what is gamma 2? Eta 1 minus eta 2 upon eta 1 plus eta 2. Straightforward? Yes. And notice gamma 2 equal to minus gamma 1. Very useful result. And this will travel a distance of theta, hits the interface at z equal to 0. A portion will come out, and then part of it gets reflected with a reflection coefficient of gamma 3, travels a distance theta, and a portion will come out, portion multiplied by tau 1 2, and what comes out is that much, and again a reflection by a reflection coefficient of gamma 2, and it keeps happening forever. If these terms tau, gamma, they're all small compared to unity, eventually this will all go to 0 and it will find a steady state. So all we have to do is add up all these factors on the left to find out what is the total gamma in, add up all the factors on the right, all those terms, not factors, they're terms, and you find out what is the value of tau. Do that now. So I have put a same picture, little compressed picture here. So gamma in is gamma 1 plus the second quantity there, tau 21 e to the power of, tau 21, tau 12 e to gamma 3 e to the power of minus j2 theta, plus the third term, tau 21, tau 12, gamma 2, gamma 3 square e to the power of minus j4 theta. Can you guess the fourth term here? Every time it is getting multiplied by a factor. What is that factor? Gamma 2, gamma 3 multiplied by e to the power of minus j2 theta. So you can straight away write many more such terms. Similarly, convince yourself tau out is given by that long equation given on the screen. Yep, good. With this, there's an infinite series, and hopefully you should be able to simplify it. And we will consider the first equation and take out the factor tau t1, tau 12, tau 21, tau 12, gamma 3 e to the power of minus j2 theta common. What we have is 1 plus gamma 2, gamma 3 e to the power of minus j2 theta plus gamma 2, gamma 3 e to the power of minus j2 theta whole square, and so on. Geometric progression straight away. And the summation is 1 upon 1 minus gamma 2, gamma 3 e to the power of minus j2 theta. 1 plus r square, so on to infinity. If r is less than 1, will be 1 upon 1 minus r straight away. And this can be simplified to this form. This is a little longish exercise, but I want you to do this. Show that gamma in is given by the last equation from the last but one equation. Now, how about tau? Tau out, that's very straightforward. Simply take tau 21, tau 32 e to the power of minus j theta common. Once again, 1 plus r square term, and the result is straightforward. No great complexity here. We managed to find tau out, gamma in using multiple reflections and converging results. Yeah, one more approach via the signal flow graph. This one is a very intricate diagram. I would like you to observe this diagram very carefully. For this, I will use a pointer this time. Hopefully, this pointer will get recorded and you will be able to see it. We have the incident wave amplitude unity. When it hits the first interface, there is a reflection of gamma 1 and a transmission of tau 21 into medium 2. And it undergoes a transmission of theta, which means e to the power of minus j theta factor, and then it comes out with tau 32 and it gets reflected by gamma 3. That is one part of the signal flow graph. Now what comes out is tau out. Similarly, if you have another unit amplitude coming here, gamma 3 times, oh, this term we don't have to worry about, we don't need it at all, and tau 3 times that incident wave from the right side will enter medium 2, and this will combine with gamma 3 whatever was coming from the top wave and travel a distance e to the power of minus j theta. This wave is going to experience a reflection coefficient of gamma 2 looking into medium 1 from medium 2, and a transmission of tau 1 2 into medium 1. So gamma 1 is the sum of these two waves. So since we are not very keen on this term here, the incident from the right side, there is nothing incident, we really don't have to worry about it. We even don't have to take into account. Now, what is gamma in? Gamma in is Mason's gain formula, gamma 1 plus this path here, tau 21 e to the power of minus j theta, gamma 3 e to the power of minus j theta, tau 1 2 back into this. That is the factor on the numerator divided by 1 minus the loop gain. What is the loop gain here? Gamma 2 e to the power of minus j theta, gamma 3 e to the power of minus j theta, which is gamma 2, gamma 3 e to the power of minus j 2 theta. Straight away you could write this equation. And how about tau out? That's very straightforward. This is the forward path gain, tau 21 e to the power of minus j theta, tau 32, which is the numerator, divided by 1 minus loop gain, gamma 2, gamma 3 e to the power of minus j 2 theta. Straightforward, one shot, we could write the result. This by far I have found the fastest way to solve the multiple interface problem. If you are comfortable with it, I would recommend please use this. The only disadvantage or danger is there is a very high chance of making a mistake while calculating the loop gains, so you should be careful about it. Now, let's take an application called quarter wave transformer. We have these three results with us. Gamma in, gamma is known in terms of gamma 1 and gamma 3, and also in terms of beta 2 and D. We'll take a situation. We have dielectric interface. So the first dielectric has a permittivity epsilon R1, second one has a permittivity epsilon R2, third one has a permittivity epsilon R3. All three are relative permittivities. So we know eta 1, eta 2, eta 3 in terms of intrinsic impedance eta naught and the relative permittivities of three media. Now choose D is equal to lambda 2 by 4. Where lambda 2 is the wavelength of that wave in medium 2. If I choose this, what will be 2 times beta 2d? It will be equal to pi. Therefore, gamma in turns out to be gamma 1 minus gamma 3 upon 1 minus gamma 1 gamma 3, because e to the power of j pi is minus 1. Now, gamma in is 0 if gamma 1 is equal to gamma 3. Straight away. What is the meaning of gamma 1 becoming equal to gamma 3? We have eta 2 minus eta 1 upon eta 2 plus eta 1 equal to eta 3 minus eta 2 upon eta 3 plus eta 2. It doesn't take million computations to show that this results in eta 2 equal to square root of eta 1, eta 3. Now if I substitute the values of eta 1, eta 2, eta 3 into this result and knock off the eta naught common factor, what I have is epsilon R2 equal to square root of epsilon R1 times epsilon R3. What's the meaning of this? If I choose three dielectric media, the middle slab has the thickness equal to lambda by 4, that is quarter wave thick, and whose permittivity is equal to square root of epsilon R1 times epsilon R3, then gamma in will be 0. This has applications. We'll come to the application. This is a diagrammatic representation of the quarter wave transformer. What we have here is, I'll take out a pointer. We have air and glass. In between we have a lambda by 4 coating. So the wave incident from air gets reflected partially from this front interface between air and the coating, and then a part of it gets transmitted, again gets re-reflected and passes back, and that is supposed to cancel the incident wave so that there is no reflection at all. So there will be reflected wave in this region, lambda by 4 coating, but there won't be any reflection in the air region. That's what we want. This simulation now shows in time what happens as the wave hits this lambda by 4 coated glass surface. So as we see that in the region 1, in the air region, since there is a pure traveling wave, there is no reflection at all. And in region 2, of course, and in the region 3, there is a glass region, of course, there won't be any reflected wave because that's extending to infinity. Where do we see the application of it? This is a very familiar one if you have your glasses, and when you look at the reflection on the glass, if you see a tint, a bluish tint, a bluish greenish tint, then you know that it has an anti-reflection coating. And this particular pair of glasses has no anti-reflection coating, and therefore you see that the intensity of reflected light is very high, number one, and it is pure white. On the other hand, here it has an anti-reflection coating, therefore the reflected light has a bluish green or cyan tint. Now, why is this tint appearing this way? This can be illustrated if I were to plot reflection coefficient as a function of frequency. This is a particular example where the thickness has been designed to be lambda by 4 at this frequency, 4 10 to the power of 14 hertz, that is 400 terahertz. This corresponds to the red light. This frequency corresponds to the frequency of red light. So what it says is that, what this picture says is that the red light will not be reflected. Therefore, what is reflected back consists of bluish and greenish tints. So those frequencies are reflected back. Therefore, the reflected light will have a color which is sort of bluish green color. Please note that this bluish green is only a representative color. For this analysis, I have made a lot of approximations and assumptions. So this is just to give you an idea that the reflected light is colored, even though the incident light is pure white. There is no color in the incident light. Now what happens if we change the thickness or change the design of that the coating, lambda by 4 coating? So now this is a case where the coating is lambda by 4 thick at 400 terahertz. Now next example where it is tuned to 600 terahertz, that is 6 10 to the power of 14 hertz. Now most of the green blue things are not reflected back. What is reflected back is a red component. So the reflected light appears reddish in color. There is no color coating on the film. It is just the way interference happens. There is a destructive interference for blue color. Therefore, whatever is remaining turns out to be reddish in color. Now let's change the design once again. Choose a thickness which is lambda by 4 corresponding to violet color. Then yes, you are right. Now the reflected light is more of yellowish or orangish in color, because there's a lot of red component and yellow component in this than the blue or violet component. So now if you go and look at any glass, optical glass, be it spectacles, camera lens or whatever, you look at the reflection, the color of the lens. If you see the color, you can almost predict what is the thickness of the coating that is being used on that particular lens. One more application, one more condition. We again start with gamma in terms of gamma 1, gamma 3. This time we'll consider a system where we have air, dielectric, air. Now, air, eta 1 is eta naught, dielectric, eta 2 is eta naught upon epsilon r2, air, eta 3 is equal to eta naught. This time we choose d equal to lambda 2 by 2, that is half wavelength slab. So this is half wavelength slab of some permittivity epsilon r2 lying in free space. And we ask the question, what is 2 beta to d? It turns out to be equal to 2 pi. Therefore, gamma in is gamma 1 plus gamma 3 upon 1 plus gamma 1 gamma 3. Now, if you see what is gamma 1, eta 2 minus eta naught upon eta 2 plus eta naught, because eta 1 is equal to eta naught. What is gamma 3? Eta naught minus eta 2 upon eta naught plus eta 2. Therefore, gamma 3 equal to minus gamma 1. Therefore, gamma in will always be equal to 0. If you choose a slab which is half wave thick, it doesn't matter what the permittivity is, you keep it in free space, it will not see any reflection. Wave will simply pass through it. Interesting? Yes, this is an idea which is used to construct a radome. So if you have an antenna and it is radiating into free space, you put a dielectric slab in front of it, which is half wave thick, then electromagnetic waves will not be seeing the dielectric slab at all. There won't be any reflection. Everything will go to the other side.